The universe around you is vast and quiet, filled with clouds of gas and dust that drift through the space between stars. These interstellar clouds, known as nebulae, are made mostly of hydrogen, with traces of helium and heavier elements created by previous generations of stars. You focus on a particular dense region, where gravity gently pulls gas particles together. As more material gathers, the cloud fragments into smaller clumps, each slowly contracting under its own weight. Over millions of years, these clumps become increasingly compact, their interiors gradually heating as gravitational energy converts into thermal energy. You sense the delicate balance between the inward pull of gravity and the pressure from the warm gas that resists collapse. Within one of these condensing clumps, the temperature rises steadily. When the core temperature reaches around 10 million degrees Kelvin, hydrogen atoms begin to fuse, forming helium through nuclear fusion. You follow the flow of energy from these reactions, radiating outward and counteracting gravity. The young star stabilizes in a state called the main sequence, where the forces of pressure and gravity maintain equilibrium. Its surface glows steadily, producing light and heat that travel across the surrounding space. You notice how this phase can last for millions or even billions of years, depending on the mass of the star. Smaller stars like our Sun can persist for over 10 billion years, while more massive stars exhaust their fuel much more quickly. As time passes, massive stars evolve more rapidly. You watch as they consume hydrogen in their cores at an accelerated rate, leaving helium ash behind. Once the hydrogen is nearly gone, the core contracts, raising the temperature until helium begins to fuse into carbon and oxygen. In stars more than 8 times the mass of the Sun, this process continues with heavier elements, forming neon, magnesium, silicon, and eventually iron. Each stage of fusion requires higher temperatures and shorter timescales, compressing the life of the star into a series of increasingly brief, energetic phases. You observe the star's outer layers expanding, cooling, and sometimes becoming unstable, creating a luminous and dynamic appearance in the sky. Iron is unique among elements produced in stellar fusion. Fusing iron does not release energy. It consumes it. You see the star's core becoming a dense iron sphere, unable to sustain fusion and support itself against gravity. Without the outward pressure from fusion, gravity overwhelms the core, pulling matter inward with tremendous force. The star's inner core contracts rapidly, compressing protons and electrons together under extreme conditions. The density increases at a remarkable rate, and the temperature soars. You are aware that this collapse happens in seconds, though the consequences will be far-reaching. The surrounding layers of the star respond violently to the collapsing core. They rebound and explode outward in a supernova, one of the most energetic events in the universe. The explosion releases a vast amount of energy, including light, heat, and neutrinos, and disperses heavy elements into the interstellar medium. You notice that these elements, created through successive stages of fusion and the supernova itself, become the building blocks for future generations of stars, planets, and even life. The spectacle is immense, yet it follows precise physical laws. You see how astronomers detect such events in distant galaxies, observing sudden brightening or neutrino bursts that travel across space. As the outer layers move away, the collapsed core remains unimaginably compact. In stars above a critical mass, gravity compresses the core to the point where neutrons form a dense, degenerate state. You consider how protons and electrons merge to create neutrons, and how the resulting neutron star contains more mass than the Sun in a sphere only about 10 to 20 kilometers across. The density is astonishing, equivalent to squeezing Mount Everest into a teaspoon. You understand that these conditions cannot be reproduced on Earth, and that neutron stars are natural laboratories for extreme physics. You notice that not all stars end this way. Stars with lower mass, like the Sun, will shed their outer layers more gently, forming planetary nebulae and leaving behind white dwarfs. Only stars with cores exceeding roughly 1.4 times the mass of the Sun, known as the Chandrasekhar limit, collapse into neutron stars. You appreciate the subtle balance of mass, pressure, and nuclear processes that determine a star's final fate. The universe provides a variety of stellar remnants, each telling a story of past energy and transformation. The gravitational field of the neutron star is intense. You imagine the pull of gravity at its surface, about 200 billion times stronger than Earth's. Any matter or radiation approaching it is strongly influenced, and light itself is slightly bent by the star's gravity. These effects are predicted by Einstein's general relativity and confirmed through precise observations of pulsars, binary systems, and X-ray emissions. You feel the rhythm of physics at its most extreme, functioning predictably even under such extraordinary conditions. Your attention turns to rotation. Many neutron stars spin rapidly, conserving angular momentum from their progenitor stars. You notice how a star's collapse reduces its radius while increasing its rotation rate, sometimes hundreds of times per second. The spinning neutron star generates magnetic fields that are trillions of times stronger than Earth's, producing phenomena such as pulsar beams. These beams, sweeping across space, allow distant observers to measure rotation periods with remarkable precision, functioning as cosmic clocks that map time and motion in a precise way. The remnants of the supernova, including the neutron star and expelled material, continue to interact with the surrounding space. Shock waves from the explosion compress nearby clouds, potentially triggering new star formation. Heavy elements carried by the ejecta mix with the interstellar medium, enriching future stars and planets with the ingredients for chemistry, geology, and biology. You sense the continuity of these processes, the interconnection between life cycles of stars, and the broader galactic environment. You reflect on the immense scales of time and energy involved. A single massive star undergoes billions of years of evolution, culminating in moments of violent transformation that reshape its surroundings. The physical principles governing these processes, gravity, nuclear fusion, electron degeneracy, and neutron degeneracy, operate reliably, offering a window into the fundamental workings of matter and energy. Observations, from nearby supernovae to distant galaxies, continually confirm the models built by astrophysicists. As the universe settles around you, you consider the contrast between the calm, slow growth of stars in their early lives and the dramatic, precise violence of their endings. The cycle of birth, fusion, collapse, and remnant formation illustrates a cosmos that is dynamic yet governed by consistent laws. You carry a sense of quiet curiosity, recognizing that each star's death sets the stage for extreme objects that push matter, energy, and physics to their limits. The dense core remaining after these transformations holds the secrets of gravitational extremes and nuclear matter, inviting you to trace the journey of matter into its most compact and energetic forms. You focus on a massive star nearing the end of its life, its core filled with iron, inert and unable to sustain fusion. The outer layers press inward, and you feel the increasing gravitational pull as the core grows heavier and hotter. Electron degeneracy, which once resisted collapse, is no longer sufficient to support the mass. You observe the slow accumulation of instability that will soon accelerate, a delicate balance giving way to unstoppable contraction. The core begins to shrink, and as it does, the density rises dramatically. Electrons are forced into protons, forming neutrons and emitting neutrinos. The collapse continues at an incredible pace, compressing matter to densities billions of times greater than anything found on Earth. You sense the almost unimaginable forces acting inwards, guided by the precise equations of quantum mechanics and relativity. Within milliseconds, the core contracts to a radius of only about 10 kilometers. At this point, neutron degeneracy pressure halts further compression. The imploding outer layers, however, continue their inward motion, crashing into the suddenly rigid core. The impact produces a shock wave that travels outward, initially losing energy as it moves through the surrounding material. Neutrinos, carrying away nearly 99% of the gravitational energy released in the collapse, interact with the stellar material, reviving the shock and driving the outer layers outward. You notice that this mechanism, predicted through detailed models and confirmed by observations of supernovae, transforms the star in a single powerful moment. The explosion releases energy on a scale almost impossible to comprehend. The luminosity temporarily outshines entire galaxies, radiating light across the electromagnetic spectrum from radio waves to gamma rays. You track the outward-moving layers, expanding at thousands of kilometers per second, carrying with them elements forged during the star's life and in the explosion itself. Carbon, oxygen, silicon, and iron, once bound in the star's core, are scattered into the interstellar medium, enriching the cosmic environment. Observing this, you understand how future stars, planets, and even the building blocks of life depend on these violent yet orderly processes. You sense the rhythmic flow of matter and energy, the way it moves outward while the core stabilizes. The ejected layers expand and cool, forming a supernova remnant that can persist for tens of thousands of years. Gas and dust mix with material already in the surrounding space, compressing nearby clouds and sometimes triggering new star formation. You follow the trajectories of these elements, understanding that supernovae are both an ending and a beginning in the cosmic cycle. Light from distant supernovae reaches observers on Earth years after the explosion, allowing scientists to measure distances across galaxies and to study the expansion of the universe. Neutrinos released during the collapse provide a quiet, nearly invisible stream of information. You imagine detectors on Earth, large tanks of water or ice, waiting to catch the faint signals as neutrinos pass through matter almost undisturbed. These detections confirm theoretical models of core collapse, giving scientists insight into processes hidden deep within the star. You notice that, despite the violence of the explosion, the physics remains consistent, predictable, and measurable. The timing and intensity of neutrino bursts match calculations based on the mass, composition, and energy of the collapsing core. Observing the outer layers, you see the formation of shock-heated shells and filaments. As the material expands, instabilities create intricate patterns of density and velocity. The chemical composition varies, with heavier elements concentrated near the center and lighter ones spread further outward. You recognize the importance of these structures for astrophysical observations. They produce spectral lines that reveal temperatures, velocities, and elemental abundances. Telescopes detect these signals, translating them into precise measurements of a star's explosive history. You feel the gentle rhythm of scientific understanding unfolding alongside the chaotic display of energy. The initial burst of radiation from the supernova fades over days and weeks, leaving a remnant glowing in X-rays, ultraviolet, and visible light. You follow how the energy continues to heat the surrounding gas, creating expanding bubbles and shock fronts visible through detailed imaging. Over centuries, these remnants mix further with interstellar material, smoothing out and blending with their surroundings. You note the cycle of creation and dispersal, each event following the fundamental laws of thermodynamics, nuclear physics, and gravity, without exception. The collapsed core remains at the center, incredibly dense and compact. For stars of sufficient mass, this becomes a neutron star. You observe that the core's density is so high that a single cubic centimeter contains hundreds of millions of tons of matter. Gravity at the surface is extreme, curving spacetime according to general relativity. The core may rotate rapidly, conserving angular momentum from the progenitor star, and generate magnetic fields trillions of times stronger than Earth's. You sense the precision of the physical principles that allow scientists to calculate mass, radius, rotation, and magnetic field, all from signals detected across space. Supernovae are not only sources of energy and matter but also tools for understanding the universe. You notice that measuring their brightness over time provides standard candles for cosmology, helping to estimate distances between galaxies. Spectroscopy reveals element formation and abundance, confirming predictions from nuclear physics and stellar evolution theory. Each supernova observed provides a carefully documented record of stellar death, guiding our understanding of both individual stars and galactic evolution. You perceive the quiet reliability of these observations, a constant thread in the dynamic universe. You pay attention to the timescales involved. While the collapse itself takes only seconds, the entire process, from hydrogen burning in the star's core to the dispersal of heavy elements, spans millions of years. This interplay of slow accumulation and rapid transformation illustrates the balance of energy, gravity, and nuclear forces. The precision of these processes, observable and measurable, emphasizes that the cosmos operates under consistent and predictable physical laws. Even as the supernova's light fades, its influence persists. Surrounding clouds of gas and dust continue to absorb energy, compress, and eventually form new stars. Heavy elements deposited by the explosion become integral to planetary formation and chemistry. The universe quietly recycles matter and energy, guided by gravity, nuclear reactions, and radiation, in a continuous flow that repeats across billions of years. You feel the calm order within the apparent chaos, the interplay of forces that leads from core collapse to explosive dispersal, shaping galaxies over vast scales. As the last shock fronts slow and the glowing remnant dims, your mind settles on the core, now a dense, compact object of immense gravity. You realize that its formation marks a threshold where matter exists in extreme states, compressing atomic nuclei into a sea of neutrons. The collapse and explosion have followed precise laws, verified by observations, simulations, and neutrino detections. In this stillness, you sense the universe's ability to transform matter and energy through predictable processes, while leaving the most compact remnants to hold secrets of density, gravity, and nuclear physics. The dense core left behind after the supernova is small, yet its mass remains immense. You focus on its composition, realizing that the matter has been compressed to densities where atomic structures can no longer exist. Protons and electrons merge, forming neutrons and releasing neutrinos. This neutronization converts the core into a nearly uniform sea of neutrons, an extremely compact state of matter that is unlike anything on Earth. The process happens almost instantaneously, and the resulting object contains more mass than the Sun, but is only about 10 to 20 kilometers across. You begin to appreciate the extraordinary density, where a teaspoon of this matter would weigh billions of tons. Gravity is relentless at the surface of this dense core. You feel the conceptual pull, thousands of billions of times stronger than Earth's gravity. Any matter approaching it would accelerate rapidly, and even light is bent by the curvature of spacetime near the surface. You observe that the neutron star's existence depends on a delicate balance between this immense gravitational pull and neutron degeneracy pressure, a quantum mechanical effect arising from the Pauli exclusion principle. Neutrons resist being squeezed into the same quantum state, creating an internal pressure that counteracts gravity. This balance stabilizes the core, preventing it from collapsing further into a black hole, as long as its mass remains below a critical limit. The core's rotation is another remarkable property. As the progenitor star collapsed, angular momentum conservation caused the spin rate to increase dramatically. You notice that a neutron star may rotate dozens to hundreds of times per second. This rapid rotation has observable consequences. It can generate beams of radiation along the magnetic axis, and it stabilizes the star's shape into a slightly flattened spheroid. These properties are measurable from Earth through careful timing of pulsars, which are rotating neutron stars that emit regular pulses of electromagnetic radiation. Observations confirm that these rotation rates match theoretical predictions based on the collapse of massive stellar cores. Magnetic fields emerge as a central feature of the neutron star. During collapse, the progenitor star's magnetic field is compressed and intensified, creating surface fields trillions of times stronger than Earth's magnetic field. These fields influence the motion of charged particles near the surface and in the surrounding space. You consider how magnetic pressure interacts with the star's rotation to produce electromagnetic radiation, and how these effects are detected by radio telescopes, X-ray observatories, and gamma-ray detectors. Each measurement provides evidence for the strength and configuration of the magnetic field, confirming theoretical models. Temperature in the newborn neutron star is extraordinarily high. Immediately after formation, the core reaches temperatures of hundreds of billions of degrees Kelvin. Neutrinos carry away much of this thermal energy, allowing the star to cool rapidly over the first minutes to hours. You notice that the surface temperature, though still millions of degrees, is far cooler than the interior. The cooling process continues over thousands to millions of years, observable as thermal X-ray emission that gradually fades. These observations provide scientists with a window into the thermal evolution and internal structure of neutron stars. You focus on the equation of state, the relationship between pressure, density, and temperature inside the neutron star. The exact properties of neutron matter at such extreme densities remain a subject of research, constrained by laboratory nuclear physics, theoretical models, and astronomical observations. You consider how variations in the equation of state influence the radius, maximum mass, and overall stability of the star. Observations of massive neutron stars, exceeding twice the mass of the Sun, place strict limits on viable models. Each measurement brings scientists closer to understanding matter at densities inaccessible on Earth. Neutrinos continue to play a subtle but critical role. During the initial formation, they escape freely, carrying information about the nuclear reactions and composition deep inside the star. Neutrino observatories on Earth, such as the Super Kamiokande detector, have captured neutrinos from supernovae, validating theoretical models of neutronization and energy transport. These nearly invisible particles allow scientists to study processes otherwise hidden from electromagnetic observation, reinforcing the remarkable predictive power of physics. You observe the immediate surroundings of the neutron star. The expelled supernova material moves outward at high velocity, eventually interacting with the interstellar medium. The resulting shock waves compress nearby clouds, potentially triggering star formation. Heavy elements from the explosion mix into the galactic environment, contributing to the chemical evolution of future generations of stars and planets. You notice that the neutron star remains relatively isolated, yet its influence extends across vast distances through gravitational effects, radiation, and magnetic interactions. The spin of the star gradually slows over time due to the emission of electromagnetic radiation and particle winds. You follow how pulsar timing arrays measure these changes with extraordinary precision. Even slight variations provide insight into the star's internal structure, the distribution of mass, and the properties of ultradense matter. Observations of pulsars with highly stable rotation periods allow scientists to test general relativity and other fundamental physics under extreme conditions, offering natural laboratories for experiments impossible on Earth. Some neutron stars exist in binary systems, orbiting companion stars. You notice that mass transfer from the companion can alter the neutron star spin rate, magnetic field, and even its thermal evolution. Accretion processes produce X-ray emission that can be measured and studied, revealing details about the star's surface layers and magnetic field geometry. These systems provide additional evidence for the physics of dense matter and allow for precise determination of mass and radius, further refining models of neutron star structure. The core's stability depends critically on its mass. If the mass exceeds roughly 3 times that of the Sun, even neutron degeneracy pressure cannot prevent further collapse. In that case, the object would become a black hole. Observations of binary systems and supernova remnants indicate that most neutron stars fall below this limit, yet the precise threshold is an active area of research. You perceive the extreme balance that defines the existence of these stars, the precise interplay of mass, density, and quantum mechanical forces that maintain their stability. Throughout the universe, neutron stars emit periodic radiation that can be detected across the electromagnetic spectrum. Radio pulsars, X-ray pulsars, and gamma-ray pulsars all provide complementary information about their spin, magnetic field, and environment. Each pulse is a data point, a rhythmic beat that reflects the underlying physics of ultradense matter, rotation, and magnetism. You feel the gentle order within this seemingly extreme environment, the consistent predictability that allows scientists to study such extraordinary objects with confidence. Even as you consider the core's extreme density and compactness, you recognize the precision of observational science in revealing its properties. The combination of rotation, magnetism, and density creates a stable system, measurable and predictable, yet pushing matter and energy to their limits. You notice how these neutron stars act as cosmic laboratories, testing the fundamental laws of physics under conditions unreachable on Earth. You reflect on the transformation from the collapsed iron core to a fully formed neutron star. The transition illustrates the universe's ability to compress matter to incredible densities while remaining governed by precise, measurable laws. You sense the continuity from the progenitor star's evolution, through core collapse, to the formation of one of the most extreme objects in existence. The principles of quantum mechanics, nuclear physics, and general relativity combine seamlessly in this process, offering a quiet but profound demonstration of nature's consistency. You focus on the surface of a neutron star, a sphere only about 20 kilometers across, yet containing more mass than the Sun. The density is extraordinary. A single teaspoon would weigh billions of tons. You visualize the matter compressed so tightly that atoms no longer exist in conventional form. Electrons and protons have merged into neutrons, forming a uniform neutron-rich core. This density is orders of magnitude beyond what can be replicated in laboratories, making neutron stars natural laboratories for physics under extreme conditions. Gravity near the surface is staggering. You sense that any object would accelerate rapidly if it approached, pulled inward by a field 200 billion times stronger than Earth's. The escape velocity is so high that even light experiences a slight curvature as it leaves the star's surface, an effect predicted by general relativity. Space and time are warped in measurable ways, and the physics governing these distortions has been confirmed through precise astronomical observations. You notice the consistency of these predictions, a reliable framework even under the most extreme gravitational conditions. You observe how the neutron star's compactness amplifies gravitational effects. Its mass is concentrated in a small volume, creating intense surface gravity while maintaining structural stability through neutron degeneracy pressure. This quantum mechanical pressure arises because no two neutrons can occupy the same quantum state, resisting further compression. You recognize the delicate balance. Too little mass and the core remains stable. Too much and gravity overwhelms the degeneracy pressure, producing a black hole. Measuring these properties requires careful astronomical techniques. You follow X-ray observations from satellites that detect emission from hot spots on the neutron star's surface. Variations in light as the star rotates reveal its size and shape. Observations of pulsars provide data on rotation, magnetic field, and mass. Binary systems offer another opportunity. By tracking the motion of a companion star, astronomers calculate the neutron star's mass with high precision. You feel the meticulous nature of these measurements, translating distant signals into concrete physical quantities. Gravitational waves provide additional insights. When neutron stars orbit each other in close binaries, they emit ripples in spacetime. You observe how detectors on Earth, such as LIGO and Virgo, measure these subtle distortions. From the waveforms, scientists extract information about mass, radius, and the internal structure of the stars. You appreciate how observations of these cosmic vibrations confirm theoretical predictions of general relativity while revealing the extreme conditions inside the stars. Surface gravity influences every physical process on a neutron star. Matter falling onto the surface from a companion or accretion disk is accelerated to immense velocities, releasing X-rays upon impact. You notice how these emissions carry detailed information about the gravitational field and the star's size. By analyzing spectra and timing of X-ray bursts, scientists infer both the pressure in the outer layers and the underlying neutron star structure. Each observation adds to the picture of one of the densest known objects in the universe. The intense gravity also bends light from the star's surface. You visualize photons emitted at different angles curving around the star, allowing observers to see slightly more than half the surface at once. This gravitational lensing is measurable, and its effects are consistent with predictions from general relativity. You feel the quiet elegance of these laws at work, operating predictably even under conditions far beyond everyday experience. You examine the relationship between mass and radius. A small change in mass can significantly alter the radius due to the extreme density. Observations of neutron stars with known masses and radii help scientists constrain the equation of state, which describes how matter behaves at nuclear densities. You follow how comparisons between models and observational data refine our understanding of dense matter, gradually revealing the range of possibilities for neutron star interiors. Rotational effects modify the apparent gravity at the surface. Rapidly spinning neutron stars experience a slight flattening at the poles due to centrifugal force, although gravity remains overwhelmingly dominant. You sense the precision required to calculate these effects. Even a rotation rate of hundreds of times per second must be integrated with the star's density and gravitational profile. Observations of millisecond pulsars confirm these predictions, providing natural clocks that demonstrate the interplay between gravity and rotation. Magnetic fields influence both the star and its surroundings. These fields, trillions of times stronger than Earth's, affect charged particles near the surface and control the flow of matter in the magnetosphere. You notice that these fields can alter radiation patterns and particle acceleration, producing detectable emissions across the electromagnetic spectrum. Careful measurement of pulse timing, spectral lines, and X-ray bursts allows astronomers to quantify the interaction of gravity and magnetism in ways that are precise and predictable. You reflect on the role of gravity in shaping the neutron star's internal structure. The balance between inward pull and neutron degeneracy pressure defines the thickness of layers, density gradients, and overall stability. The internal composition may include exotic phases of nuclear matter, such as superfluid neutrons and superconducting protons, predicted by theoretical models and indirectly supported by observations. You feel the calm certainty of physics, providing clear descriptions of matter under conditions unimaginable on Earth. Temperature also interacts with gravity. Newly formed neutron stars are initially extremely hot, with temperatures of billions of degrees Kelvin in the core. Rapid cooling occurs as neutrinos carry energy away, while the surface remains millions of degrees. Gravitational confinement ensures that this heat is contained and radiated in a controlled manner, contributing to observable X-ray emissions. You follow how scientists track cooling over decades and centuries, gradually revealing the thermal history of these dense objects. Even the motion of surrounding matter is governed by gravity. In binary systems, accretion disks form as matter spirals inward, accelerated by the neutron star's immense pull. The orbital speed and energy release are directly linked to the gravitational field. You observe that careful timing of X-ray bursts and orbital motion provides data on mass, radius, and surface gravity. Each measurement reinforces the understanding of extreme density and the strength of gravitational effects. You consider how these extreme densities and gravitational forces set neutron stars apart from any other known objects. Their predictability, despite the extremity of conditions, allows scientists to test theories of nuclear physics and general relativity simultaneously. Observations across multiple wavelengths, combined with gravitational wave data, provide a comprehensive view of the star's properties. You feel the rhythm of physics at its most extreme, orderly and measurable even in the presence of immense forces. The dense core's compactness continues to influence space far beyond its immediate surface. Light, matter, and radiation passing nearby experience measurable effects, confirming theoretical predictions with high precision. You sense that the interplay between density, gravity, and rotation is not random but follows predictable, testable rules. Each observation provides a link between the star's internal state and its observable properties. Even as you consider the immense gravitational pull and ultra-high density, you notice that the star's existence is stable and persistent over millions of years. Gravity and degeneracy pressure maintain the structure, while rotation and magnetic fields add complexity without destabilizing the system. The neutron star stands as a quiet testament to the interplay of fundamental forces, compressing matter to extremes while remaining fully observable and understandable through precise science. You focus on a neutron star rotating hundreds of times per second. Its magnetic field, trillions of times stronger than Earth's, is not aligned with its rotational axis. This misalignment causes beams of electromagnetic radiation to sweep across space, similar to a lighthouse beam rotating over the sea. You understand that when one of these beams intersects with Earth, telescopes detect a pulse of radio, X-ray, or gamma-ray emission. The pulses are extremely regular, with periods that can be measured to microsecond precision. You notice the quiet consistency of this rhythm, a steady beat in the cosmic environment. The creation of a pulsar begins with the rotation of the collapsed core. Conservation of angular momentum dictates that as the progenitor star shrinks from thousands of kilometers to only tens of kilometers, its spin rate increases dramatically. You follow the process in your mind, visualizing the acceleration from a slow stellar rotation to a period of milliseconds or seconds. This rapid spin, combined with the intense magnetic field, produces the precise emission patterns that define a pulsar. Observations confirm these predictions, matching the theoretical models of rotation and magnetic field interactions. Magnetic fields are central to the pulsar phenomenon. The misalignment between the magnetic and rotational axis channels charged particles along the field lines. These particles emit radiation as they accelerate, producing the detectable pulses. You observe how the magnetic field shapes the surrounding magnetosphere, controlling particle motion and radiation patterns. Scientists measure the timing and intensity of these pulses, which provides detailed information about the star's magnetic field strength and configuration. The measurements are consistent across multiple wavelengths, confirming the reliability of theoretical models. Pulsars act as remarkably precise cosmic clocks. Some rotate with periods of just a few milliseconds, maintaining stability over millions of years. You imagine astronomers timing these pulses to study the rotational period and its gradual slowdown. The loss of rotational energy occurs as the neutron star emits radiation and particle winds. This gradual breaking is measurable and allows scientists to estimate the star's age, often referred to as the characteristic age. You appreciate the predictability of these measurements, revealing the physics of energy conservation and electromagnetic emission under extreme conditions. Binary pulsars provide additional insights. When a pulsar orbits another star, precise timing of its pulses can detect tiny variations caused by orbital motion. You observe how the arrival times of pulses shift due to the Doppler effect, revealing the star's velocity and orbital parameters. In some systems, general relativity predicts the emission of gravitational waves, causing the orbit to gradually shrink. Observations of these changes confirm theoretical predictions, providing experimental tests of gravity under conditions far beyond those achievable on Earth. The rotation of a pulsar can occasionally undergo sudden changes, called glitches. You notice that the star's rotation rate increases slightly, a phenomenon believed to result from interactions between the superfluid interior and the rigid crust. Monitoring these glitches provides scientists with indirect information about the internal structure and state of matter inside neutron stars. Each observation adds a piece to the puzzle of understanding matter under extreme densities and pressures, complementing other measurements of mass, radius, and magnetic field. You watch how pulsars influence their surroundings. The radiation and particle winds emitted by the star can create nebulae, accelerating particles in the interstellar medium and producing synchrotron radiation. The Crab Nebula, for example, is powered by a pulsar whose rotational energy drives continuous emission. You follow the flow of energy from the neutron star to the surrounding gas, noting that these interactions are entirely governed by known physical laws, including electromagnetism and particle dynamics. Observational data from radio, X-ray, and gamma-ray telescopes confirm these processes with precision. Some pulsars emit across multiple wavelengths simultaneously. Radio pulsars produce regular pulses detectable by ground-based radio telescopes. X-ray pulsars emit due to hot spots on the surface or from material accreting from a companion star. Gamma-ray pulsars produce high-energy radiation from the magnetosphere. You recognize that studying pulsars across the electromagnetic spectrum provides a complete picture of the star's magnetic field, rotation, and emission mechanisms. Each wavelength contributes unique information, reinforcing the understanding of these complex systems. Pulsar timing arrays use multiple pulsars to detect minute variations in arrival times, allowing scientists to probe gravitational waves and interstellar medium effects. You notice that even tiny irregularities in pulse timing are measurable, offering insight into space-time perturbations over vast distances. The consistency of these cosmic clocks, maintained across millions of years, provides a stable framework for astrophysical observations and tests of fundamental physics. Each pulse carries data about the star, its environment, and the universe itself. The predictability of pulsars allows their use in practical applications. Navigation, for example, can rely on pulsar timing as a natural reference system in deep space. You consider how their regularity surpasses artificial clocks in some respects, providing a method for precise position measurements across the galaxy. Observations from multiple pulsars allow triangulation, turning these distant neutron stars into a network of natural beacons. The process is entirely governed by physics, from rotation and magnetism to electromagnetic emission, and validated by careful observation. You reflect on the contrast between the extreme conditions at the neutron star surface and the regularity of the pulses reaching Earth. The material is ultradense, gravity is immense, and magnetic fields are trillions of times stronger than familiar experience. Yet the pulses arrive with remarkable consistency. The interplay of quantum mechanics, general relativity, and electromagnetism creates a system both extreme and predictable. Observations of pulsars confirm this duality, offering insights into matter, energy, and space-time that are inaccessible in terrestrial laboratories. Even as some pulsars slow or cease emission over millions of years, the existing population provides ongoing insight into neutron star physics. You watch how rotational energy, magnetic fields, and emission patterns evolve, giving scientists a temporal perspective on extreme matter and energy. The regularity of pulses and the occasional glitches together reveal the internal composition, thermal evolution, and magnetic dynamics. You sense the calm order beneath the high-energy, high-density environment, the universe speaking through predictable, measurable pulses of light. You consider the historical discovery of pulsars. The first detection in 1967 revealed rapidly repeating radio signals, initially mysterious but soon understood as emission from rotating neutron stars. Observations have since confirmed thousands of pulsars across the galaxy, each one a laboratory for extreme physics. The precision of theoretical predictions and observational techniques reinforces the reliability of the models, demonstrating that even under conditions far beyond everyday experience, physics remains consistent and testable. You focus on a neutron star with a magnetic field far stronger than any on Earth or anywhere in the solar system. This is a magnetar, a type of neutron star whose field can reach 1,000 trillion times stronger than Earth's magnetic field. You imagine the field lines extending far into space, shaping the motion of charged particles and bending the paths of radiation. Electrons and protons near the surface move along these lines, spiraling at incredible speeds and emitting high-energy photons detectable as X-rays and gamma rays. The physics governing these interactions is precise and measurable, relying on electromagnetism and quantum mechanics. The surface of a magnetar is a place of extreme conditions. You sense that magnetic pressure dominates the outer layers, even influencing the crust of the star. This pressure can deform the star slightly, creating stress in the rigid neutron-rich crust. Occasionally, this stress is released in sudden shifts, producing bursts of radiation observed on Earth. These outbursts are extremely energetic, but they are fully explained by the known properties of matter under such magnetic and gravitational forces. Observations of these bursts provide scientists with direct information about the field strength and the physics of the crust. The magnetic field also affects the vacuum around the star. In the intense field, space itself behaves differently, influencing the propagation of light. You notice that photons can split or change polarization in ways that are detectable with precise instruments. These quantum electrodynamic effects, predicted decades ago, are now confirmed by X-ray observations. The ability to test these extreme physical predictions reinforces your understanding that even the most violent environments follow predictable laws. You follow the energy stored in a magnetar's field. The total magnetic energy can exceed the star's rotational energy, making magnetars unique among neutron stars. This energy can be released suddenly in the form of giant flares, which radiate more energy in a fraction of a second than the sun emits in 100,000 years. Observatories across the globe and in space detect these events, measuring the spectrum, timing, and intensity of emitted radiation. Each observation matches theoretical models of magnetic reconnection, crustal stress, and particle acceleration, confirming the underlying physics. Magnetars are relatively rare. Only a small fraction of neutron stars exhibit such extreme fields. You note that these stars are born from massive progenitors and rapidly spinning cores, where conditions during core collapse can amplify magnetic fields to extraordinary strengths. The combination of rotation, collapse, and convective motion in the early seconds after formation determines the final field intensity. Observations of young magnetars, coupled with modeling, allow scientists to reconstruct these formation processes with remarkable precision. Bursts from magnetars are detected primarily in high-energy X-rays and gamma rays. You imagine satellites orbiting Earth, equipped with sensitive detectors that record these sudden emissions. Each burst provides a precise timestamp and energy profile. By analyzing multiple bursts over time, scientists infer properties such as the field strength, surface temperature, and even the geometry of magnetic loops. The data are consistent with theoretical expectations, revealing the interplay of gravity, nuclear matter, and electromagnetism in these extreme stars. The strongest magnetars produce what are called giant flares, extremely brief yet immensely powerful events. You notice that during a flare, the star emits more energy in a second than most stars do in a year. This energy is carried away primarily as X-rays and gamma rays, but the magnetic field shapes the ejection of particles as well. By studying the timing, spectrum, and decay of these flares, astronomers confirm models of magnetic field instability and energy release. Even the most extreme events remain predictable within the framework of physics. Magnetar fields can also influence surrounding space. Charged particles trapped in the magnetosphere follow twisted field lines, generating currents and radiation. The interaction of these fields with interstellar material can produce detectable radio emission, further extending the star's observable influence. You notice that the reach of a magnetar's field is immense, but governed entirely by known laws of electromagnetism. Models predict particle motion, radiation emission, and field decay, all confirmed through careful measurement. The decay of a magnetar's field occurs over thousands to millions of years. As the star slowly loses magnetic energy, bursts become less frequent, and rotation gradually slows. You sense the gentle timing of these processes, governed by energy conservation, resistive decay, and the interaction between field and crust. Observations of older magnetars confirm the predicted evolution of field strength and activity. The data provides scientists with a long-term picture of how extreme magnetic fields change over time, giving insight into the life cycle of these extraordinary stars. Magnetars also provide natural laboratories for studying physics under conditions unattainable on Earth. The combination of ultra-strong magnetic fields, high density, and gravity creates a setting where quantum electrodynamics and nuclear physics intersect. You consider that photons, electrons, and neutrons behave differently under these conditions, but always according to measurable, predictable laws. Observations of bursts, surface emission, and magnetospheric effects allow scientists to test models of matter, radiation, and magnetism at unprecedented extremes. You observe how the alignment of magnetic and rotational axes affects emission. In some magnetars, the axes are closely aligned, producing steady emission with minimal pulses. In others, misalignment creates periodic bursts, observable as repeating pulses in X-rays. These variations provide insight into the star's geometry, rotation, and field configuration. Measuring these patterns requires careful timing and spectral analysis, revealing details about field structure, surface activity, and the interaction between rotation and magnetism. The energy stored in a magnetar's field influences its thermal evolution. The magnetic pressure contributes to heating the crust, while particle acceleration in the magnetosphere produces radiation that can be measured remotely. You notice that this energy interacts with cooling processes, including neutrino emission and surface radiation, creating a delicate balance. Observational data confirm that theoretical models accurately predict temperatures, emission spectra, and evolution over time. The extreme physics remains consistent and testable, reinforcing the reliability of scientific understanding. Even rare, catastrophic events, such as giant flares capable of affecting nearby space, are consistent with physical laws. You consider that these flares provide opportunities for multi-wavelength observations, linking X-ray, gamma-ray, and radio measurements. Each detection refines understanding of magnetar activity, energy storage, and particle interactions. Scientists are able to reconstruct events in detail, demonstrating the predictive power of astrophysics and the robustness of models for ultra-strong magnetic fields. You reflect on the contrast between the intensity of magnetar fields and the precision with which they are measured and understood. Despite the extreme strength and energy, all behavior is explained by known physics, including quantum mechanics, electromagnetism, and nuclear structure. Observations confirm predictions from theoretical models, illustrating the power of science to describe even the most extreme natural phenomena. The magnetic field, energy release, and influence on surrounding matter form a continuous cycle of observation and understanding. Each burst, flare, and particle emission provides measurable data. These measurements reveal not only the properties of the magnetar itself but also fundamental physics, from the behavior of matter under ultra-high density to the effects of quantum electrodynamics in strong fields. You sense the universe's consistent rules at work, even under conditions that seem beyond imagination. You begin by considering a neutron star in a binary system, orbiting a companion star. Its motion is influenced by gravity, causing the companion to move in response. By carefully tracking these motions, astronomers can calculate the neutron star's mass using Newtonian mechanics and general relativity corrections. You notice that even slight variations in the companion's velocity provide precise information, because the star's gravitational pull is so strong. Observations of these orbital dynamics, often using radio or optical telescopes, reveal the mass of the neutron star with remarkable accuracy. X-ray bursts offer another method for measurement. Some neutron stars accumulate matter from a companion star, forming a thin layer on the surface. When this matter reaches a critical temperature and density, nuclear fusion ignites, producing a burst of X-rays. You follow how the spectrum and timing of these bursts are analyzed to estimate the radius and surface gravity. By comparing the observed flux with theoretical models of the star's atmosphere, astronomers determine how large the star must be to produce the measured emissions. Each observation aligns closely with physical predictions. You observe the significance of pulse timing from rotating neutron stars. Millisecond pulsars emit highly regular pulses of electromagnetic radiation. When these pulses travel through space, their arrival times can be measured with microsecond precision. Slight variations in timing, caused by motion in a binary system or gravitational effects, allow scientists to determine both mass and orbital parameters. You sense the delicate precision required. Each pulse is a tiny, reliable signal that contributes to understanding the star's properties. Gravitational waves add another layer of measurement. When neutron stars orbit each other in tight binaries, they emit ripples in spacetime. Detectors such as LIGO and Virgo record these waves, revealing the masses and tidal interactions of the stars. You notice that the shape of the gravitational wave signal encodes the stars' radii as well as their masses. By analyzing the waveform, scientists can extract precise information about both stars simultaneously, confirming predictions from general relativity. Observing these waves allows a direct measurement of properties that would otherwise remain inaccessible. NICER, an X-ray observatory on the International Space Station, offers yet another approach. You imagine it pointing at a pulsar, measuring X-ray emission from rotating hotspots on the surface. The variations in intensity as the star spins provide information about the shape and size of the star. Light bending due to the star's strong gravity allows emission from parts of the surface that would otherwise be hidden. By modeling these effects, astronomers can determine the radius and mass, combining observational data with relativistic calculations. Each dataset refines the accuracy of the measurement. You follow how spectroscopy provides complementary information. Observing absorption lines in X-ray spectra allows scientists to measure gravitational redshift, a shift in photon energy caused by the star's intense gravity. This redshift directly depends on the ratio of mass to radius. By analyzing these shifts in combination with timing and flux measurements, a consistent picture emerges. You sense the convergence of multiple techniques, each confirming the others, creating confidence in the derived values. Binary systems exhibit phenomena that further refine measurements. Eclipsing binaries, where the companion passes in front of or behind the neutron star, allow precise determination of orbital inclination. You notice that these geometric measurements, combined with timing and spectroscopic data, provide mass estimates that are independent of some modeling assumptions. The combination of methods ensures that the final measurement is reliable and grounded in multiple independent lines of evidence. You observe the significance of mass distribution. Most neutron stars have masses around 1.4 times that of the Sun, but some exceed 2 solar masses. These measurements constrain the equation of state, the relationship between pressure and density inside the star. The mass and radius determine the maximum pressure achievable, offering insight into nuclear interactions under extreme densities. You sense the subtle interplay between observation and theory. Precise measurements guide understanding of matter at densities far beyond terrestrial experiments. Observations of isolated neutron stars, not in binaries, also provide information. Surface emission, cooling rates, and thermal spectra can reveal radius estimates. You follow how combining these data with distance measurements allows inference of surface area and therefore radius. While these measurements are more challenging, they complement binary observations, providing cross-checks and expanding the dataset. The consistent agreement across methods strengthens confidence in the derived properties. You notice how gravitational lensing plays a role in measurement. Light emitted from the star's surface is bent by its intense gravity, allowing distant observers to see regions of the surface that would otherwise be hidden. This effect, predictable from general relativity, must be incorporated into models of pulse profiles. You consider the precision required in these calculations, where small changes in bending angles affect the inferred radius. Observations match theoretical predictions, reinforcing the reliability of both the measurements and the underlying physics. Timing irregularities, including glitches, also contribute to understanding. Sudden changes in rotation provide insight into the interior structure and the distribution of mass. You follow how these events are used to model the moment of inertia and the mass-radius relationship. Each glitch, although subtle, offers an opportunity to test theoretical models, connecting rotational dynamics with dense matter physics. Observations over years allow patterns to emerge, confirming the consistency of models. X-ray burst oscillations reveal additional detail. The rotation of hot spots during bursts produces a periodic signal in the observed X-ray flux. Modeling the amplitude and phase of these oscillations allows constraints on radius and surface gravity. You sense how rotational modulation, combined with gravitational light bending, encodes geometric information about the star. Careful analysis yields measurements that complement independent techniques, reinforcing the emerging picture of neutron star structure. You reflect on the combination of methods. Timing, spectroscopy, gravitational waves, and X-ray pulse modeling converge to provide accurate mass and radius measurements. Observational evidence is consistent with predictions from nuclear physics, relativity, and astrophysics. You feel the steady reliability of science, where extreme objects like neutron stars can be characterized with remarkable precision. Each data point, each measurement, adds to a coherent understanding of matter under extraordinary conditions. The precision of these measurements allows scientists to explore the limits of nuclear matter, test models of ultradense cores, and refine the maximum possible mass of neutron stars. You notice that each neutron star studied provides a natural experiment, offering data that connect microscopic nuclear physics with macroscopic astrophysical phenomena. Observations guide theoretical models, while models interpret the measurements, creating a continuous cycle of understanding. You recognize that measuring neutron star mass and radius is more than recording numbers. It is an exercise in connecting physics across scales. From nuclear forces to gravitational interactions, from electromagnetic radiation to relativistic effects. Each measurement reinforces the predictive power of physics, demonstrating that even under extreme conditions, nature follows precise and measurable rules. You begin by considering the matter inside a neutron star. At the core, densities exceed those found in atomic nuclei, creating an environment impossible to replicate in laboratories. The equation of state, or EOS, describes the relationship between pressure, density, and temperature in this extreme matter. You understand that the EOS determines the star's structure, how mass and radius relate, how the core responds to stress, and how the star evolves over time. Observations of neutron stars provide natural constraints on these models, offering insight into fundamental physics at densities far beyond Earth's reach. Different theoretical models predict different behaviors for ultradense matter. Some suggest a stiff EOS, where pressure rises quickly with density, producing larger radii for a given mass. Others suggest a soft EOS, where pressure rises more slowly, resulting in smaller, more compact stars. You follow how astronomers compare these predictions with observational data, examining pulsar masses, radii, and rotational properties. Each measurement either supports or constrains certain models, narrowing the range of possibilities for the star's internal composition. Observations of massive neutron stars are particularly important. A neutron star exceeding 2 solar masses, for instance, places a lower limit on the stiffness of the EOS. You notice that such measurements rule out models that cannot support this mass without collapsing into a black hole. Similarly, precise radius measurements constrain the compressibility of matter at nuclear densities. By combining mass and radius data, scientists gradually construct a map of allowable equations of state, connecting macroscopic observables to microscopic nuclear interactions. You consider the role of gravitational waves in refining the EOS. When neutron stars in a binary orbit merge, the emitted waves carry information about the star's deformability under tidal forces. This tidal deformability depends on the internal structure and pressure profile, which are directly related to the EOS. You follow how waveforms detected by LIGO and Virgo reveal these subtle effects, providing new constraints on the stiffness or softness of ultradense matter. Each merger adds a piece to the puzzle, helping scientists refine models with unprecedented accuracy. Thermal emission from neutron stars also contributes to understanding the EOS. X-ray observations of cooling neutron stars provide information about surface temperatures and thermal gradients. These measurements, in combination with mass and radius estimates, inform scientists about heat transport in the crust and core. The behavior of matter under such high density influences the star's thermal evolution, confirming predictions from theoretical models. You sense the subtle but crucial connection between temperature, pressure, and density, all encoded in the EOS. Superfluidity and superconductivity within neutron stars offer additional insight. Neutrons in the inner core may form a superfluid, while protons become superconducting. These states affect heat capacity, viscosity, and rotational dynamics. You notice that observations of glitches in pulsar rotation provide indirect evidence for these exotic states of matter. Each glitch, combined with rotational timing data, constrains the physical properties of the star's interior, revealing behavior governed by quantum mechanics under extreme conditions. You explore how magnetic fields interact with ultradense matter. In magnetars, for example, the magnetic field can contribute to pressure and influence the structure of the crust. You notice that these fields modify the EOS locally, affecting emission, particle motion, and even the geometry of the star's surface. Observations of X-ray bursts, pulse profiles, and spectral lines allow scientists to quantify these effects. Each measurement strengthens understanding of how electromagnetic forces interact with matter at nuclear densities. Laboratory experiments provide complementary information. Nuclear physics experiments on Earth measure interactions between neutrons and protons at high density, helping to calibrate models of the EOS. You observe how these terrestrial measurements, when combined with astronomical data, create a coherent picture. The behavior of matter at densities slightly below those in neutron stars serves as a bridge, connecting experiments with the extreme environments found in the cosmos. Rotational dynamics of neutron stars further constrain the EOS. Rapidly spinning pulsars experience centrifugal forces that affect their shape, slightly flattening the poles. You notice that the maximum spin rate a neutron star can sustain without breaking apart depends on the stiffness of the EOS. Observations of millisecond pulsars approaching these limits help scientists eliminate models that cannot support such rotation. This connection between rotation, structure, and density provides a natural laboratory for extreme physics. Binary neutron star mergers reveal additional information about ultradense matter. During the inspiral phase, tidal effects and gravitational radiation encode details about the star's internal pressure profiles. After the merger, the remnant may briefly form a hypermassive neutron star before collapsing into a black hole. You follow how observations of post-merger electromagnetic and gravitational signals constrain the maximum mass a neutron star can support, providing further insight into the EOS. Each detection contributes to a growing understanding of nuclear physics under extreme conditions. You consider the uncertainty in the EOS. While observations provide strong constraints, extreme conditions allow multiple plausible models. Scientists use Bayesian statistical methods to combine information from different sources, mass measurements, radius estimates, X-ray observations, and gravitational waves, producing probability distributions for allowable EOS parameters. You sense the careful balance between measurement and theory, where predictions are refined by accumulating evidence. The study of neutron star oscillations offers additional constraints. Stellar quakes and oscillatory modes, detectable through subtle variations in emission, reveal the star's internal structure and elastic properties. You follow how these observations connect directly to the pressure-density relationship, confirming or refining theoretical models. Each measurement is a natural probe of matter under conditions far beyond what could be recreated in a laboratory. You notice that the EOS has implications beyond individual stars. It affects neutron star populations, maximum masses, rotational limits, and even the properties of gravitational waves produced in mergers. Understanding the EOS allows scientists to predict and interpret phenomena across the cosmos, connecting nuclear physics with astrophysical observations. Each observation, combined with theoretical modeling, reduces uncertainty and deepens knowledge. Through the combination of observational techniques, timing, spectroscopy, thermal emission, and gravitational waves, you watch as the properties of ultradense matter become gradually constrained. You appreciate the precision of this work. Even the densest, most inaccessible matter is subject to careful measurement and modeling. Observations and theory work in harmony, providing a clear window into the physics of neutron star interiors. You reflect on the profound insight provided by the EOS. By understanding how pressure and density relate under extreme conditions, scientists unlock the behavior of matter at nuclear densities, the limits of neutron star mass and radius, and the stability of these extraordinary objects. Observational data from multiple sources converge to create a coherent picture, confirming that even under extreme conditions, the laws of physics remain consistent and measurable. You begin by observing a system of two neutron stars locked in mutual orbit. Each star exerts a powerful gravitational pull on the other, creating a precise, repeating orbital dance. The gravitational field around each star is intense, curving spacetime as predicted by Einstein. You notice that as the stars orbit, they emit energy in the form of gravitational waves, ripples in the fabric of spacetime that propagate outward at the speed of light. This energy loss causes the orbit to gradually shrink, drawing the stars ever closer together in a slow, steady inspiral. The inspiral process takes millions to billions of years, but its effects are measurable. You observe that the orbital period decreases very slightly over time, a change detectable through precise pulsar timing. These variations match exactly the predictions of general relativity. By monitoring the pulses from one star, astronomers measure shifts caused by the changing gravitational field of its companion. The timing differences are minuscule, but accumulated over years, they reveal the star's gradual approach, confirming the theory with remarkable accuracy. Gravitational waves carry information about the masses and internal structure of the stars. You notice that the amplitude and frequency of the waves increase as the stars spiral closer. Low-frequency waves dominate initially, while higher-frequency waves arise near the final stages. The waveform encodes details about each star's mass, radius, and tidal deformability. Scientists use these signals to infer the equation of state of neutron star matter, linking the external motion to the extreme physics inside the dense cores. Each measurement provides a natural experiment in conditions unreachable on Earth. The waves themselves are incredibly weak when they reach Earth. You imagine laser interferometers like LIGO and Virgo detecting changes in distance smaller than the diameter of a proton across kilometers-long arms. Despite this faintness, the signals are clear because of careful isolation, precise timing, and repeated measurements. The detected waves match theoretical predictions, confirming that gravitational waves behave exactly as Einstein described. Each detection reinforces confidence in our understanding of space-time, mass, and energy. As the stars approach their final moments, their orbital velocity increases dramatically. You notice that the gravitational waves increase in both frequency and intensity, producing a characteristic chirp signal. This signal allows scientists to estimate the time remaining before merger. Observations show that the energy emitted in gravitational waves exceeds the total energy output of ordinary stars by orders of magnitude, yet it remains fully explained by relativity. Each waveform encodes precise details of mass, orbit, and internal structure. During the merger itself, immense forces act on the neutron stars. The cores collide, producing a hypermassive neutron star for a brief moment, or collapsing rapidly into a black hole depending on the total mass. You follow the release of gravitational energy, which is complemented by electromagnetic radiation across the spectrum. Gamma rays, X-rays, optical and radio signals provide a multi-messenger perspective, confirming the sequence and dynamics of the merger. Each observation reinforces the connection between gravity, nuclear physics, and radiation processes. Heavy elements are produced during these events. Neutron-rich material is ejected at high velocity, undergoing rapid neutron capture, or R-process nucleosynthesis. You notice that elements like gold, platinum, and uranium form in this environment. Observations of kilonovae, transient optical and infrared signals following mergers, reveal the mass, velocity, and composition of ejected material. These data match predictions from nuclear physics models, showing that mergers are a major source of heavy elements in the universe. The timing of electromagnetic signals relative to gravitational waves provides additional insight. Gamma-ray bursts are detected within seconds of the merger, while optical and infrared emission evolves over days. You follow how these timings allow scientists to determine distances, energetics, and ejecta properties. Each measurement aligns with theoretical models, showing that even the most violent astrophysical events unfold according to predictable physical laws. Binary neutron star systems also provide opportunities to study relativistic effects. You notice that phenomena like periastron precession, Shapiro delay, and gravitational redshift are measurable in pulsar timing. These effects, predicted by general relativity, are amplified in systems with strong gravitational fields. Observations confirm the precise curvature of spacetime around massive, dense objects, providing natural laboratories for testing gravity under extreme conditions. Each measurement is a demonstration of the theory's predictive power. You observe the diversity of binary neutron star systems. Some orbit rapidly, producing strong gravitational wave signals, while others are wider and evolve slowly. The mass ratios, spins, and orientations of these binaries vary, creating a rich population for study. Each system contributes unique information, from mass distribution to tidal effects, allowing scientists to refine models of neutron star formation, evolution, and interaction. The ensemble of observations provides a statistically robust understanding of these extreme systems. The post-merger remnant, whether a massive neutron star or black hole, continues to radiate energy. You notice that the hypermassive neutron star may survive for milliseconds to seconds before collapsing, emitting gravitational waves in the process. The observed frequencies provide information about the equation of state, internal structure, and stability limits of dense matter. Electromagnetic observations complement this, revealing how energy is redistributed into ejecta, radiation, and particle acceleration. Each measurement confirms predictions from high-density nuclear physics and relativistic dynamics. You consider the historical significance of the first observed merger of two neutron stars in 2017. Gravitational waves were detected by LIGO and Virgo, followed within seconds by gamma rays and later by optical and infrared observations. This multi-messenger detection confirmed that mergers produce heavy elements, gamma-ray bursts, and observable kilonovae, uniting decades of theoretical prediction with direct evidence. You sense the quiet precision of science. The universe communicates through measurable signals, fully described by known laws of physics. Even before merger, subtle interactions influence the system. Tidal forces deform the stars, transferring energy and angular momentum. You notice that these deformations alter the gravitational wave signal slightly, encoding information about the internal structure. Observing these effects allows scientists to constrain the equation of state and understand matter at nuclear densities. Each pulse, each gravitational ripple, is a message about the interior of the neutron stars, revealing a hidden world through indirect but precise measurements. The study of binary neutron stars connects multiple areas of physics. General relativity describes the gravitational wave emission. Nuclear physics governs the properties of matter inside the stars. Electromagnetism explains the bursts of radiation observed. By combining observations from all these domains, scientists build a complete, consistent understanding of these systems. You notice that even the most complex events are entirely measurable and predictable, a testament to the robustness of physical law. You reflect on the slow, steady spiral of neutron stars. Over millions of years, these compact objects orbit each other, emitting energy in predictable patterns. Observations capture the culmination of this process, confirming both the predictions of relativity and the behavior of matter under extreme density. The combination of gravitational waves and electromagnetic signals provides a full picture of the system, demonstrating how the universe communicates its rules through measurable phenomena. You begin by observing two neutron stars approaching the final moments of their spiral. Their orbital velocity increases as gravity draws them closer, and the frequency of gravitational waves rises. You notice that these waves carry energy away, forcing the stars into an ever tighter orbit. The last seconds of this spiral occur at a fraction of the speed of light, and yet, each movement follows precise physical laws. The interaction of gravity, mass, and angular momentum dictates the sequence of events with predictable accuracy. At the moment of collision, the stars' cores interact violently. You observe that the outer layers are ejected at high velocity, creating a cloud of extremely dense, neutron-rich matter. This material undergoes rapid neutron capture, or R-process nucleosynthesis, forming heavy elements such as gold, platinum, and uranium. You notice that this is not theoretical conjecture. It is measured through spectroscopy of the light emitted by the ejected material. The wavelengths and intensities correspond precisely to predictions of nuclear physics, confirming the synthesis of these elements during the merger. Simultaneously, a burst of gravitational waves emanates from the system. You feel the rhythm of the waves, encoding information about the masses, radii, and internal structure of the colliding neutron stars. The waveform carries subtle details of the tidal forces and the stiffness of the matter inside each star. By analyzing these signals, scientists can reconstruct the collision with astonishing precision. Every peak and trough in the waveform corresponds to a real aspect of the star's behavior, providing a natural laboratory for studying ultradense matter. Light across the electromagnetic spectrum accompanies the merger. Gamma rays are often detected within seconds, forming short gamma-ray bursts. X-rays follow as the remnant stabilizes, and optical and infrared emission develops as the ejected material cools and expands. You notice that each wavelength provides different information. Gamma rays trace the initial energy release, while optical and infrared emissions reveal the composition, velocity, and quantity of ejecta. Observations match detailed predictions from models of kilonovae, reinforcing the reliability of theoretical physics. You consider the timescales of these signals. Gamma-ray bursts last seconds, gravitational waves last minutes in the sensitive frequency bands, and optical emission evolves over days. Each signal is precisely predictable given the properties of the merging stars. By combining multi-messenger observations, scientists obtain a comprehensive picture of the event, measuring both dynamic and compositional properties. This integrated approach allows determination of masses, radii, ejecta mass, and even the production rate of heavy elements in the universe. The ejecta expand rapidly into space, interacting with surrounding material. You observe shock waves and heating which contribute to the emission of light. The temperature and opacity of the ejecta influence the observed color and brightness of the kilonova. Spectroscopic analysis confirms the presence of heavy elements, matching nuclear reaction networks calculated from first principles. Each observation aligns closely with theoretical models, demonstrating that even the most extreme collisions produce predictable, measurable phenomena. Neutrinos are also emitted during the merger. Though weakly interacting, they carry energy and information about conditions deep within the remnant. You notice that neutrino detectors on Earth, while capturing only a tiny fraction of these particles, provide complementary data on the physics of the merger. The emission of neutrinos confirms models of energy transport and the behavior of ultradense matter under extreme temperatures. Each neutrino detection offers subtle but critical insight into the inner workings of the merger. You follow the remnant object. Depending on the total mass, it may form a hypermassive neutron star for a short period or collapse immediately into a black hole. The properties of the remnant affect the emission of gravitational waves and electromagnetic radiation. You notice that even these extreme outcomes are predictable within general relativity and nuclear physics models. Observations of the remnant's evolution allow scientists to test theories of maximum neutron star mass, equation of state, and collapse dynamics. The kilonova emission provides a direct window into nucleosynthesis. You observe that our process elements are ejected with velocities reaching tens of thousands of kilometers per second. The abundance patterns match the predictions of nuclear reaction networks for neutron-rich matter. This confirms that neutron star mergers are a primary site for the formation of heavy elements in the universe. Each observation quantifies the contribution of these events to cosmic chemical evolution, connecting distant astrophysical phenomena to the material composition of planets and stars, including Earth. Magnetic fields influence the dynamics of the merger. Strong fields guide particle motion, amplify turbulence, and affect the geometry of ejecta. You notice that simulations incorporating realistic magnetic fields produce results that match observed light curves and spectra. The interplay of gravity, nuclear physics, and electromagnetism produces an emergent behavior that can be directly measured. Observations confirm that the physical laws governing these processes remain consistent, even in extreme conditions far beyond human experience. You watch the sequence of events unfold with remarkable precision. Each merger produces a consistent pattern. In spiral, collision, gravitational wave emission, gamma-ray burst, ejecta expansion, optical emission, and eventual remnant formation. Scientists analyze multiple events to confirm this sequence, refining models and improving predictions for future observations. You sense the order within apparent chaos. Each outcome follows known physics, measured and verified across the electromagnetic and gravitational spectrum. The detection of gravitational waves combined with electromagnetic signals allows distance measurement. By comparing the amplitude of gravitational waves with the observed brightness of the kilonova, astronomers calculate the distance to the source. This provides an independent method for measuring cosmic distances, complementing other techniques such as supernova observations or redshift measurements. Each merger thus contributes not only to understanding dense matter but also to refining knowledge of cosmic expansion. Observing these events over time reveals the frequency of neutron star mergers in the universe. You notice that this rate informs models of chemical enrichment, binary star evolution, and gravitational wave event predictions. Each detection adds data to a statistical framework, confirming the expected distribution of masses, spins, and orbital parameters. The consistency between observation and prediction strengthens confidence in both astrophysics and nuclear physics models. You reflect on the precision required for these observations. Instruments must detect tiny perturbations in spacetime, faint gamma-ray bursts, and rapidly evolving optical signals. Yet, despite the extreme conditions and immense energies, all measurements align with theoretical predictions. Observational astronomy, combined with computational models, allows you to follow every step of the merger and the production of heavy elements with scientific certainty. You consider the broader significance. Neutron star mergers demonstrate how matter behaves at nuclear densities, how energy is transported, and how the universe produces its heaviest elements. By combining gravitational waves, electromagnetic signals, and neutrinos, scientists gain a complete, precise understanding of these extraordinary events. Each merger serves as a natural experiment in extreme physics, revealing processes that cannot be reproduced in laboratories, yet remain fully measurable and predictable. You begin by observing a neutron star shortly after its formation. Its rotation is rapid, sometimes hundreds of times per second. This incredible spin results from the conservation of angular momentum as the progenitor star collapses. You notice that the star's intense gravity and compact radius amplify this effect. As the core shrinks, the spin rate increases, producing a millisecond pulsar. These early rotations are steady but gradually change over time, as the star emits radiation and loses energy. The star emits electromagnetic radiation from its magnetic poles. If the magnetic axis is misaligned with the rotation axis, the radiation sweeps across space like a lighthouse beam. You follow how the emission of this energy gradually slows the star's rotation. This spin-down process is measurable through long-term pulsar timing. By recording the arrival times of pulses over years, astronomers can calculate the rate at which the star loses rotational energy. Even tiny changes, imperceptible in a human lifetime, accumulate and reveal the gradual evolution of the star. Magnetic fields play a critical role in the evolution of spin. The intense field interacts with charged particles in the star's magnetosphere, transferring angular momentum to the surrounding environment. You notice that stronger magnetic fields produce faster spin-down rates. Observations of pulsars with different field strengths confirm the predicted relationship between field intensity and rotational deceleration. These measurements demonstrate how electromagnetic processes shape the long-term evolution of neutron stars. Some neutron stars experience sudden changes in rotation called glitches. You observe these abrupt events, where the spin rate temporarily increases. Glitches provide insight into the internal structure of the star. They are thought to result from interactions between the superfluid interior and the crust. By studying these glitches, astronomers infer the properties of matter deep within the neutron star, connecting rotational behavior with the physics of ultradense cores. In binary systems, neutron stars can experience a different evolutionary path. When a companion star transfers mass to the neutron star, angular momentum is also transferred. You follow how this process spins the neutron star up, creating a recycled pulsar. These millisecond pulsars exhibit extremely regular pulses and rapid rotations, often exceeding hundreds of revolutions per second. Observations show that the process depends on the rate of mass transfer, the magnetic field, and the duration of accretion. Each factor can be measured, providing a comprehensive understanding of spin evolution in binaries. You notice that the spin period of neutron stars can range from milliseconds to several seconds. Younger pulsars tend to rotate faster, while older stars slow gradually. This distribution is confirmed through population studies. Each measurement provides data for models of angular momentum loss, magnetic field decay, and binary interactions. Over millions of years, the interplay of these factors shapes the rotational history of the neutron star population. Observational evidence comes from multiple wavelengths. Radio observations capture the regular pulses of many stars. X-ray timing reveals the behavior of accreting pulsars. Optical observations of companion stars in binaries provide mass transfer rates and orbital dynamics. You follow how combining these data allows astronomers to reconstruct the spin evolution over cosmic timescales. Each observation confirms theoretical models of rotational deceleration, accretion-induced spin-up, and glitch phenomena. The slow loss of rotational energy is not uniform. You observe variations caused by changes in magnetic field strength, interactions with the interstellar medium, and structural adjustments in the star's interior. Timing measurements reveal both gradual trends and short-term anomalies, each explained by known physics. You notice how these observations validate predictions from magnetohydrodynamics and nuclear physics, demonstrating the predictive power of scientific theory applied to extreme conditions. Millisecond pulsars in globular clusters offer another perspective. In these dense stellar environments, interactions with other stars and close encounters influence spin and binary properties. You follow how observations of pulsars in clusters reveal the combined effects of mass transfer, stellar encounters, and tidal interactions. The precise timing of pulses allows measurement of orbital decay and gravitational influences, providing a detailed picture of evolutionary pathways. You reflect on the long-term evolution of solitary neutron stars. Over millions to billions of years, they gradually spin down, emitting radiation and losing rotational energy. Eventually, some may become undetectable, their magnetic fields weakening and pulses fading below observational thresholds. You notice that even in isolation, the physical principles governing rotation, energy loss, and magnetic interaction remain consistent, producing predictable, measurable outcomes. Population studies reveal the statistical patterns of spin evolution. Younger neutron stars cluster at shorter spin periods, while older stars occupy longer periods. Recycled pulsars occupy a separate region of parameter space, highlighting the influence of binary interactions. You observe that this distribution aligns with theoretical predictions, confirming that spin evolution is governed by angular momentum conservation, magnetic field decay, and accretion processes. You follow the feedback loop between observation and theory. Each pulsar provides precise timing measurements that test models of rotational dynamics. Glitches inform internal structure, magnetic fields guide spin-down rates, and binary interactions illustrate accretion-induced spin-up. By combining these observations, astronomers construct a coherent picture of how neutron stars evolve over millions of years. You sense the precision and predictability of this natural clockwork. You notice that the spin of neutron stars also influences gravitational wave emission in binaries. Faster spinning stars have slightly altered quadrupole moments, affecting the gravitational wave signal during in-spiral. By observing pulsar spin and binary orbital parameters, scientists refine models of gravitational waveforms. Each measurement confirms the interconnection between rotation, magnetic fields, and gravitational physics, showing that even subtle properties produce measurable effects across cosmic scales. Over time, the spin evolution leads to diversity among neutron stars. Some remain isolated with slow rotation, others become rapidly spinning recycled pulsars, and some undergo glitches that provide insight into internal physics. Observations reveal that each star's evolution is determined by initial mass, rotation, magnetic field, and environmental interactions. You notice the predictable yet varied outcomes, a reflection of the precise but dynamic processes governing these objects. You reflect on the broader implications. The evolution of spin connects the microscopic physics of matter in the star's interior with macroscopic phenomena like pulse emission and gravitational waves. By tracking rotation over millions of years, scientists gain insight into superfluidity, magnetic field decay, accretion, and nuclear matter properties. Observations, verified across multiple techniques, provide a calm, consistent understanding of these extraordinary objects. You begin by approaching a neutron star with the awareness that you are entering a domain no laboratory on Earth can replicate. Its density, magnetic field, and gravity combine to create an environment more extreme than any particle accelerator or fusion experiment. You recognize that neutron stars serve as natural laboratories, offering direct insight into physics at its limits. Each observation allows scientists to test theories that cannot be probed in terrestrial conditions. You first notice the density, so high that a single teaspoon of neutron star matter outweighs mountains. This density compresses matter to a state where nuclei merge, forming neutrons and exotic particles. You observe how this environment allows scientists to test nuclear physics at supernuclear densities. By analyzing pulsar timing, starquakes, and glitch behavior, researchers infer the stiffness of the equation of state. Each rotational irregularity reveals how matter responds to pressure 10 trillion times greater than in an atomic nucleus. The crust of the neutron star becomes your next focus. It is rigid yet permeated by superfluid neutrons that flow without friction. You recognize that the behavior of this superfluid, combined with the star's crystalline crust, allows physicists to study quantum mechanics on a macroscopic scale. Superfluid vortices pin to the crust and suddenly unpin in glitch events, providing clues to quantum behavior under immense pressure. You realize that each glitch is a message from the star's interior, revealing properties of superfluidity that laboratories cannot reproduce. You then turn your attention to magnetic fields. Neutron stars possess fields 1 trillion times stronger than Earth's, especially magnetars. These extreme fields influence atomic structure itself, stretching atoms into elongated shapes and altering electron behavior. You observe how these conditions test quantum electrodynamics, revealing how photons behave in magnetic environments so intense that vacuum polarization becomes significant. Through X-ray and gamma-ray observations, scientists detect bursts that confirm theoretical predictions about magnetic reconnection and vacuum birefringence. Gravitational physics becomes your next lens. Neutron stars warp spacetime so intensely that their gravitational potential allows researchers to test general relativity in the strong field regime. You notice how binary pulsars emit gravitational waves that gradually shrink their orbits. By measuring orbital decay over decades, astronomers verify Einstein's predictions with extraordinary precision. The timing measurements become a bridge between relativity and observation, confirming the theory in environments far more extreme than the solar system. You sense how neutron stars in merging binaries provide the most dramatic tests of gravity. When two neutron stars spiral together, they emit detectable gravitational waves. Observations of these events allow researchers to measure tidal deformability, offering new constraints on the equation of state. You follow how differences in compactness and stiffness alter the waveform. Each merger provides a direct probe of the physics of dense matter, connecting gravitational wave astronomy with nuclear physics. The surface of the neutron star provides another window into extreme physics. Around the magnetic poles, charged particles accelerate to near-light speeds, emitting radiation across the electromagnetic spectrum. You recognize that these processes allow scientists to test magnetohydrodynamics under extreme pressure and density. Observations of hotspots, pulse profiles, and thermal cooling curves give insight into heat transport and magnetic structure. Each dataset refines theoretical models of surface composition and magnetic topology. Cooling behavior offers yet another opportunity for discovery. Newly formed neutron stars cool rapidly as neutrinos carry away energy. By measuring the temperature decline over years or decades, researchers gather evidence about neutrino emission processes. You observe how these measurements connect neutron star cooling with particle physics, including the behavior of exotic particles such as hyperons or deconfined quarks. Each temperature curve becomes a trace of the fundamental particles within the core. Neutrino physics also finds a natural laboratory here. During a supernova, the newborn neutron star emits a burst of neutrinos that carry information about core collapse mechanisms and matter at extreme densities. You recall how observations from SN 1987A confirmed predictions about neutrino behavior, validating theoretical models of stellar death and neutron star formation. Each neutrino detection becomes a rare glimpse into the conditions deep within the star. You move to consider rotational dynamics once more. The clock-like regularity of pulsars enables extraordinary precision tests of physics. Some pulsars maintain timing stability comparable to atomic clocks, allowing scientists to detect gravitational waves, measure variations in fundamental constants, and monitor the influence of interstellar plasma. You appreciate how each precisely timed pulse helps test the structure of spacetime and refine measurements of cosmic distances. Binary pulsars expand this laboratory further. Systems containing neutron stars and white dwarfs, or two neutron stars, act as natural detectors of gravitational interaction. You observe how the relativistic precession of orbits, time dilation effects, and Shapiro delay align with predictions from general relativity. By analyzing these effects, scientists test theories of gravity beyond Einstein's. Each measurement becomes part of an ongoing effort to understand how gravity behaves in the most extreme conditions known. You then explore the possibility of exotic matter at the core. Under immense pressure, quarks may become deconfined, forming quark matter or strange matter. These states remain hypothetical, but neutron stars provide the only place in the universe where they may exist naturally. Observations of mass, radius, tidal deformability, and maximum rotation rates all contribute to the search for signatures of exotic cores. You sense how each measurement brings science closer to uncovering whether nature forms quark stars or hybrid stars. You find that neutron stars also help test the behavior of matter under rapid rotation. Some spin hundreds of times per second, approaching the limit at which centrifugal force would disrupt the star. By measuring the fastest known pulsars, scientists constrain how stiff the equation of state must be to prevent breakup. Each rapid rotation becomes a demonstration of how matter behaves when pushed to its absolute limits. High-energy emissions provide another window into physics. Magnetar bursts, pulsar wind nebulae, and X-ray pulsations reveal how energy is transported and released in strong magnetic fields. These emissions allow researchers to study particle acceleration, magnetic reconnection, and plasma physics on scales unimaginable on Earth. Each observation of a sudden flare or steady pulse reveals new details about the underlying physical processes. You reflect on how neutron stars unify diverse fields of physics. Nuclear physics, quantum mechanics, relativity, hydrodynamics, particle physics, and astrophysics all converge in these objects. Each observation provides a data point that strengthens our understanding of nature across scales, from subatomic particles to galaxies. You feel the harmony of the cosmos expressed through the behavior of these compact stars. You let your thoughts settle into the quiet of the cosmos, holding the long journey you have taken through the world of neutron stars. You picture the vast interstellar clouds where stars first emerge, cold and dark until gravity gathers them into dense cores. You reflect on how gentle those early stages seem when compared to the later extremes that shape neutron stars. This contrast lets you appreciate the span of physical processes that lead from soft molecular clouds to some of the densest objects in the universe. You recall the steady glow of ordinary stars accomplishing fusion in their cores, producing the stable energy that supports planets and creates the chemical ingredients for life. You remember how, when massive stars exhaust their lightest elements, they move through heavier stages of fusion, each one requiring higher temperatures and pressures. You sense that these steps, though violent in their internal forces, obey clear physical rules. Nothing happens suddenly without a cause. Each stage unfolds within predictable boundaries defined by nuclear physics. Your reflection brings you to the moment when massive stars collapse, the instant when gravity overtakes all resistance and forces matter inward with unimaginable pressure. You understand how these events create neutron stars, leaving behind cores where the density exceeds that of any material found elsewhere. You feel calm knowing that these extreme objects do not defy scientific principles but instead demonstrate them at their limits. Their existence is a direct expression of how matter behaves when compressed far beyond familiar scales. You think again about magnetic fields and how magnetars take those fields to extremes. Their magnetic strength reshapes atomic structure, influences particle interactions, and produces high-energy bursts observable across vast distances. You appreciate that the behavior of these fields, though intense, still follows known laws of electromagnetism and quantum electrodynamics. Each observation confirms predictions rather than contradicting them, offering a reassuring sense of order even in the most powerful magnetic environments known. As your thoughts move to measurements, you recall how scientists determine mass and radius using simple, precise observations. Binary systems allow timing techniques that reveal how gravity shapes the motion of stars around each other. Thermonuclear bursts offer ways to estimate surface properties, while gravitational waves provide new measurements of how these stars deform under tidal forces. You appreciate how these techniques reduce uncertainty and allow the nature of neutron stars to be described with increasing confidence. You linger for a moment on the equation of state, the relationship between pressure and density deep inside these stars. You reflect on how different models predict different internal structures and how observations slowly narrow the possibilities. Each pulsar measurement, each gravitational wave detection, each radius estimate contributes another piece to the puzzle. You find comfort in this gradual tightening of knowledge, a slow and steady approach to understanding matter at its densest form. Your attention shifts to the orbital motion of binary neutron stars, graceful yet governed by the steady emission of gravitational waves. You reflect on how general relativity predicted this loss of orbital energy long before it was observed. When you think about how precisely timing measurements have matched theoretical expectations, you feel a sense of calm trust in the reliability of physical laws. You understand that the universe behaves consistently across time, distance, and scale. You revisit the moment when two neutron stars finally merge. You think of the gravitational waves that record their inward spiral, the rise in frequency that marks their final approach, and the sudden quiet that follows their collision. You reflect on how that event sends light across the universe, producing a kilonova whose brightness reveals the creation of heavy elements. You feel a quiet amazement at how neutron-rich matter, compressed for so long, becomes the birthplace of gold, platinum, and other heavy materials. You pause on the idea that neutron stars serve as natural laboratories. You have seen how they test gravity, nuclear physics, particle physics, and quantum mechanics without contradicting any of them. You recognize that the universe itself supplies the environment scientists cannot replicate on Earth, and instruments positioned across space and on the ground gather the data needed to interpret these natural experiments. This realization deepens your appreciation for the unity between observation and theory. You reflect on the role of precision, how accurate timing, careful spectroscopy, and sensitive gravitational wave detection allow scientists to see details once thought unreachable. You understand that the more precise the measurement, the more clearly the universe reveals itself. Your awareness settles into the idea that knowledge grows not from speculation but from detailed observation that steadily narrows uncertainty. This process feels both slow and reliable, moving forward with the same calm persistence that guides natural systems. You consider how neutron stars evolve over long periods. Their rotation slows as they emit radiation, their magnetic fields change, and their internal structures gradually cool. You reflect on how recycled pulsars regain their speed through accretion and how long-term timing observations reveal these shifts. You find a gentle reassurance in the idea that even these extreme objects follow clear paths defined by the physics of energy loss and angular momentum transfer. You bring to mind the merging systems once more, not for their violence but for the clarity they bring. The gravitational waveforms reveal the internal structure of neutron stars, while the electromagnetic emission tells scientists about the matter ejected into space. You appreciate that these events let multiple types of observations work together, forming a complete picture. This cooperation between light and gravity strengthens your awareness of how much can be learned when different tools gather evidence from the same event. As your reflection deepens, you return to the beginning of the journey, back to the simple idea that neutron stars represent extremes that still follow natural laws. You see how each stage, from star formation to merger, fits into a structure shaped by gravity, nuclear forces, and the stable behavior of matter. Nothing in this path requires guesswork. Everything follows patterns that can be measured, modeled, and confirmed. You rest in the understanding that the universe's most intense phenomena are still governed by order. You let your mind drift across all these extremes, moving gently from the soft collapse of gas clouds to the dense interiors of neutron stars, their magnetic storms, their bursts of radiation, their precise timing, and their merging orbits. You feel a calm sense of awe at how much can be understood from careful observation alone. You recognize that the universe is vast and sometimes violent, yet it behaves according to principles that remain consistent across every environment you have explored.